Okay, looking at the number of participants, I think we can start. There are few persons missing, but probably fine. So we will start the third lecture by Massimo, and then we will all reconvene for the discussion session after the lecture, so with a 1 hour break. Please, Massimo, you can.
Okay, thank you very much, Diego. Hello, everybody. So the plan today is to complete our survey of the linear matter power spectrum. If you remember, last time I was starting to introduce the baryonic acoustic oscillations, and we will start from there. Then I will show quite quickly, I would say, but we can discuss more if you want during the discussion section, the effect of neutrino masses on this matter power spectrum. You remember that up to now, we have not considered neutrinos, and matter was just cold dark matter plus baryons. Then we will go a little bit closer to the real world, the real observations. So let me just summarize this part of the lecture with some observational effects. You will see what it means. One effect is that we are looking, for instance, in redshift space to infer the distances of the objects that we look at. So our inference of the real distance from us of this object is, is polluted by this effect. Another effect is that we are looking at baryonic matter, stars, galaxies, and not dark matter. This introduces another complication. And then there are also some complications due to the statistics of the object that we are observing. And I hope at the end I will be able to cross the linear frontier, and I will start to introduce the main nonlinear effects that will occupy us for the remaining lectures. Okay, I just recalled the last equation that I wrote, in which basically, this is, if you remember, delta gamma now is delta rho over rho for the photons, but since the photons and baryons are tightly coupled, this is also modulo a factor, which is 3/4 the delta rho over rho for the baryons. And the equations that I just wrote contains, the most relevant term in this equation is this pressure term, which depends on the sound speed. And the sound speed, if you remember, is just 1/3 sound speed square, 1 plus R, where R is the baryon to photon ratio in energy units. Baryon to photon energy density. So what happens, and then we will see a movie. Today is a movie day, just to have a quick physical intuition of what's going on, is that in this fluid, this baryon photon fluid, this baryon to photon fluid, because there is pressure, then you have the possibility of having sound waves, which are sustained actually by the pressure of the fluid. And so as a first intuitive explanation of what's going on, you imagine that this sound waves, acoustic waves, will travel at the speed given by CS square until, since the beginning, until the epoch in which baryons and photons decoupled. So as a first approximation, you can imagine that these speeds travel with this speed, which is slowly changing with time, and then at a certain point, suddenly the sound speed goes to 0 because the coupling between the baryon and photon goes to 0, and so these waves are somehow frozen at a characteristic length. And this characteristic length is just the space traveled by these waves up to matter radiation decoupling. And this will leave an imprint on the distribution of matter in the universe That is a very precious source of information because it tells us, as I will show, it gives us a way to actually infer the expansion history of the universe independently of other probes, like, for instance, supernova of type 1a. So I would ask Francesco now to start a movie in which what I am describing is very intuitive, I would say, and then I will discuss in more detail. So before you start, just show the first image. So what you are seeing here, please don't start. What we are seeing here is a matter over density. So imagine there is this primordial gravitational potential that has some fluctuations which were imprinted by inflation. And then we are concentrating on one single point in which the gravitational potential has some well. And so matter, dark matter, is starting to accumulate because of gravity towards this point. So that you will see the cold dark matter density grow because matter is coming from nearby regions. So please start. But you also see, can you stop, please? Sorry. You also see an outgoing wave. And this outgoing wave is precisely the wave in the matter, in the baryon photon fluid, which first is also accumulated towards the overdensity, but then because of pressure, pressure reacts to the amplification of density, and so you have an outgoing wave at the speed of sound, which is given by the equation that I gave you before. So the propagation of the wave lasts until recombination. At recombination, you see you have a sudden stop of this wave because this wave basically the velocity of this wave drops to 0 immediately. Now imagine there are many points like this in the sky. So what you see, can you stop here, please? A situation in which you have these overdensities in matter, and there is also a scale which is imprinted in this distribution. That is to say, there are some centers of, if you want, accumulation, and then a given distance away from these centers, there is a sphere of enhanced matter density. So what we are looking for is precisely this scale in the distribution of matter in the universe today. Can you please go on? So as a consequence, you will have a situation in which you have these frozen waves, and on top of these frozen density locations, the probability of forming stars and galaxies increases with respect to the average. So if you now compute the 2-point correlation function, if you remember the meaning, the physical meaning of the 2-point correlation function is, if you want, the probability of finding a structure at a given distance from a given point, or probability to find a structure at a given distance as a function of distance. So what you will find is that at a scale given by this separation, we find a peak in the 2-point correlation function because at that scale there is an enhanced probability of having formed overdensity and then of having formed galaxies and galaxy clusters. Now, okay, you can stop. So this scale is imprinted in the distribution of matter. Is a scale that today that we can compute from first principles because what it enters are just two very simple, very solid, I would say, informations. One is about the sound speed, which depends on the ratio between baryons and photons. And the other one is the decoupling scale. The decoupling scale is also a very robust prediction in standard cosmology. And then if you modify the background cosmology or the physics that you have in the background, of course, you also modify this scale. But in general, it's something that we can compute very, very, very reliably, I would say. So, and today this scale, was forgetting, it is a number which is about 110 megaparsec, again divided by this small h. So today, this is the number of the scale. In the past, it was smaller, but just by naive rescaling due to the expansion. So now, going in a little bit more detail, okay, this is another view of what's going on, in which we have the different components that make up the universe separated, so you can see what happens to the different components. The most important ones are colder matter, baryons, and photons. So in the first plot, in the first plot, which is taken at redshift 6000, that is much before decoupling, what you see is an overdensity in dark matter, which is the black one. Okay, this is in real space, not in Fourier space, so it's really a density profile, which you see is growing because of some gravitational potential here, which is lower than elsewhere. And then you see, okay, these two curves here now are perfectly overimposed one over the other. One is photons and the other one is baryons. They are tightly coupled at this epoch, so they basically have the same profile. And then you also have neutrinos. For the moment, just forget about neutrinos. So what you have is that as time passes, okay, dark matter still tends to accumulate in the same region, whereas, as we show in the movie, the the baryon photon fluid is going far away from the overdense region because of pressure, because of acoustic sound. And then at some point between here and here, you have decoupling. And what happens is the baryon and photon becomes two separate fluids. Baryons are simply frozen to the region that they reached by the time of decoupling, whereas photons now are free to propagate, to free stream in the universe. And they will quickly, I mean, escape this overdense region and diffuse basically across all the universe as neutrinos. Okay, so if you see the density profile of neutrinos, which are relativistic at this epoch, and photons very quickly trace one another. On the other hand, if we keep our attention on the baryons, then you see that we have, okay, the central overdensity in dark matter and the baryon overdensity. After decoupling, baryons behaves exactly as cold dark matter. So the two fluids now basically trace one another. They contribute to the gravitational potential in the same way. So at the end, if you even if they start from different initial conditions, the distribution, the mass profile, if you want, of the distribution of density of baryons and cold dark matter is the same. And as you see, just as you saw in the movie, there is an enhanced probability of finding matter at 100 megaparsec, which corresponds to this 110 megaparsec divided by h that I mentioned before. So now, pictorially, what we are looking for is a pattern in the distribution of matter in the universe, in which, again, there is an enhanced probability. I mean, you give me a galaxy, there is an enhanced probability to find galaxies at 110 megaparsec over h from it. And the important point is that this scale is imprinted at every epoch. Okay, this is really a relevant point. And this is the same scale. This is the same. I mean, it's the same physics which plays the driving role in creating the CMB anisotropies. So the game here is to read the scale at different redshifts, from very low redshifts, I mean, close to today, back up to the CMB scale, back to decoupling. Okay. For what concerns matter distributions, that actually what we are looking for, I mean, this is, for instance, the region of sky which was measured by Sloan Digital Sky Survey. You see that The baryon acoustic oscillation scale corresponds to this, this red circle inside the sky, so you need big volumes. We will make an estimate later on how big should be the volume of my survey to measure accurately enough this scale. And this is the measured two-point correlation function again by Sloan. By the way, this effect was first detected in 2005 by Sloan, and it is now measured by many other surveys. Sorry, this is not Sloan, this is BOSS actually. This is for the correlation function, and this is for the matter power spectrum. Okay, in the matter power, so what you see is a peak in the correlation function. Then in the matter power spectrum, that is the Fourier transformation of the Fourier transform of the correlation function, you will see oscillations, and this is what you see. What you see here is the power spectrum divided by some smooth spectrum in order to enhance this feature. Okay, because it's a small feature because its amplitude goes like the density in baryons over the density in cold dark matter. Since the baryons is around 1/5 of cold dark matter, is it's even less. It's a very small effect. Okay, and last thing, okay, and this is what you really want to do if you want to use the BAO to do the baryon acoustic oscillation to do cosmological tests. So this is where we stand now. Basically, these are different redshifts. These are different measurements on the large-scale structure, so low redshift measurements from BOSS galaxies, quasars, and so on and so forth. And what you're really measuring is the angle under which you see these features at different redshifts. The angle is given here. I mean, the expression that you are looking for is given here. It's just the ratio between the co-moving sound horizon scale with this 110 megaparsec divided by the co-moving distance to redshift z. So it's here that the cosmology dependence enters. I mean, the dependence on z of this quantity depends on this integral on the Hubble parameter, the time-dependent Hubble parameter. So depending on the cosmology, you get different angles at different redshifts. And what you see overimposed here is what you expect by, I mean, the one in this plot is what you expect by assuming the Planck best fit cosmology, the best fit cosmology that you infer from CMB measurements. Okay, you see, we would like to improve these measurements, both on the measurement side and, of course, on the computational side. And tomorrow, or maybe the day after tomorrow, I will show you how it is crucial to keep under control these nonlinear corrections, actually not at a finite order, like one or second or third order in perturbation theory, but actually you have to resum some effects in perturbation theory to all orders. And this only, I mean, this procedure allows you to have, say, a 1% accuracy on the determination of the scale, on the acoustic scale from this kind of measurements and observations. So I think I will stop here for the BAOs. Other questions? So just remember that from the theory point of view, from the theory side, our goal is to compute this correlation function, or if you want, these wiggles in the matter power spectrum at a percent level accuracy. This will be one of the tasks that I will illustrate in the following lectures. Okay. So now we move to another effect. So this effect, as I was mentioning last time, adds basically tiny wiggles on the matter power spectrum. Here, starting from 0.0 h inverse megaparsec in K. Okay, now I will tell you about another effect, which okay, should be there. We know that it is there, but it has not yet been measured. That is the effect of massive neutrinos, the effect on neutrino masses on the matter power spectrum. And we will see that neutrino masses basically will affect your power spectrum, again on the small scale region, by depleting it, I mean lowering it a little bit in a way which is proportional to the sum of the neutrino masses. Okay, so now the subject is neutrino masses. And let me just recall some very basic fact about standard model neutrinos in cosmology, of course. So I will assume three neutrino species. They are coupled by the weak interaction. So first of all, neutrinos were in equilibrium in the high temperature universe, but at some point they decoupled because weak interaction became slower than the expansion rate of the universe. So in order to determine when this happened, as Marco already explained, you have to, the first thing you have to do is just a dimensional analysis. So the rate, a typical rate which keeps neutrinos coupled by weak interaction, will go as a Fermi constant to the power 2, of course. Then it is a rate, and then since the rate have the dimension of mass, and this is the dimension of mass to the minus 2 to the power 2, so minus to the minus 4, you need here t to the 5. And this is the typical weak rate. And then you ask, when does this guy becomes less than h, double parameter? And again, during radiation domination, this is just given by g star 1/2 t squared divided by m Planck divided by m Planck. So you see that below some temperature, neutrinos will decouple because this weak rate is decaying very fast with temperature. And what you find is that the temperature of below which weak interaction decouple is about 0.8 MeV, okay, order 1 MeV, okay? So for these temperatures, say for T less than T weak, neutrinos are decoupled. So the important point is that 1 MeV is much larger than the present bound, upper bound on the neutrino mass, which is something, experimental bound, something of order of the EV, electron volt. So what we learn from this is that neutrinos, when decoupled, all the three types of neutrinos are relativistic. Okay? They decouple, they don't talk to the universe anymore. The only thing that they feel is gravity, of course, and the expansion of the universe. So to start with, we have a gas of neutrinos at this temperature. And they basically, this temperature basically just decreases because of the expansion of the universe. So a result in general in standard cosmology is that the neutrino temperature at a given redshift Z is just given by the photon temperature at the same redshift times a constant of order 1, which is just 4/11 the 1/3. And the fact that this is not 1 is simply due to the fact that after decoupling, after neutrino decoupling, electrons become non-relativistic, so they start to annihilate one another, and they give entropy. I mean, the annihilation goes into photons and not to neutrinos. So the photon fluid is a little bit hotter than the neutrino one by this effect. But Okay, and so these neutrinos has an average momentum of order, again, T nu of Z. If you want to be precise, there is a number here, which is just given to the fact that you compute this average momentum from a Fermi-Dirac distribution, and then you get, but just by doing the integral of the Fermi-Dirac distribution function, you get this number here. But the important point is that this guy here, as we see, is proportional to the photon temperature today times 1 plus Z. Okay, the photon temperature at redshift Z is just the photon temperature today multiplied by redshift plus 1. So as time passes, redshift decreases, so the neutrinos become less and less relativistic. So at a certain point, this ratio will become less than 1, while it was much larger than 1 at the beginning because the temperature was higher than the neutrino mass. And then, so you have a transition for the neutrinos from a relativistic to a non-relativistic species, okay? So the first question is, when does it happen? When does neutrinos become non-relativistic? Standard model neutrinos, I'm not talking about more exotic stuff. So, well, we have just to use these equations here. And the result, which I will now explain, is that if the neutrino mass for a given species is between 10 to the minus 4 electron volt and about 3.1 electron volt, then in this mass range, in which, by the way, all the neutrinos of the standard model are, the neutrinos become non-relativistic after matter radiation equivalence. Okay? How do you get this? Well, you just get this 3.1 by plugging in basically the temperature at the equivalence between matter and radiation. This gives you this number. And this number you get by the same computation where you put the actual temperature of the photons. So if the neutrino mass is in this range, they are non-relativistic today, but they became non-relativistic after equivalence. So all of them either still relativistic or they became, or at least at most one of them can be non-relativistic. So let me say better. So what do we know about neutrino masses experimentally? Well, we know basically there are 3 neutrinos and okay. So if this is the neutrino mass values, okay, we know there are, okay, 3 eigenstates of the neutrino masses. And what we know from experiments are this interval, basically, and this interval, but we don't know the absolute scale. So let me assume that one of the 3 neutrinos is exactly massless today, which is still a possibility. So what we can have is either this situation or this situation in which you have 1 massless neutrinos and 2 massive ones, okay? So what we know is that this difference, this delta m nu, is something of order say 10 to the minus 3 electron volt, 8 in 10 to the minus 3 electron volt. Okay, so this next to the licensed neutrino is already heavier than the lower bound in the inequality that I wrote before. So at most, 1 neutrino is still relativistic, But at least two of them are non-relativistic today, okay? Or we can have all three neutrinos which are non-relativistic because this, all these things can be shifted up, okay? So we are sure that the standard model neutrino are there in high quantity, in large quantities, and are non-relativistic, and became non-relativistic after matter radiation equivalence. So what does it imply? So again, so neutrinos become, let's just follow one neutrino species, they become relativistic somewhere between here and say today, no? Okay. Let's call this epoch A non-relativistic. What does it mean if we follow this specific neutrino family? Then it enters matter epoch as a radiation fluid, I mean, as a relativistic fluid. So its perturbation will not grow as the perturbation in matter and in barium later on. Okay. The reason is that, okay, it's relativistic, so it travels at the speed of light. It means that if it sees a gravitational potential, well, basically it is relativistic, so it escapes the gravitational potential. It doesn't want to be squeezed by gravity. Okay, and only after this neutrino becomes non-relativistic, it starts to behave like normal cold dark matter. So it starts to participate to the growth of structure as baryons and cold dark matter. Okay, so what is the effect of this on the matter power spectrum? So imagine there is now, say, a total matter fluid, which is given by the sum of the cold dark matter plus the baryon plus the neutrino fluid, okay? And only, I mean, at late time, this part of the neutrino fluid becomes non-relativistic. So now we are interested in the total dark matter perturbation. So you can see that it is given by Fc delta C plus F baryon delta baryon plus F neutrinos delta neutrinos. This is delta matter, where these are the fractions of the total matter fluid in cold dark matter, baryons, and neutrinos. So for instance, F nu is just rho nu divided by rho matter, rho cold dark matter plus rho baryon plus rho neutrino. So what is the effect of the presence of some quota of the total matter budget in terms of massive neutrinos? Okay. Well, you can already understand it from this expression, if you can see it. I'm not sure because okay, look at this expression at the different scales. Okay, there is a scale, a relevant scale here, which is K non-relativistic, which is the scale, the largest scale that these neutrinos can have traveled before becoming non-relativistic. That is to say, these neutrinos basically cannot form any structure, cannot contribute to the formation of structure below these physical scales. Or if you want, for K, in Fourier space, larger than this K non-relativistic. So if I'm looking at K larger than K non-relativistic, as a first approximation, I would say that the delta neutrino would be 0. On the other hand, for k smaller than k non-relativistic, then neutrinos were simply behaving as cold dark matter in this case. So delta nu in this case would exactly be of the same order of cold dark matter and baryons. Okay. So compared to, so what you see is that compared to the total matter power spectrum, I'm sorry, this doesn't write at all. Okay, now the delta matter power spectrum would be for small scales, where basically you have delta C of the same order of delta B, much larger than delta neutrinos. So I just put this guy to 0, and is given by 1 minus f nu delta C, because delta C and delta B are equal, and the sum of the three f would give 0. On the other hand, and so this is for k much larger than k non-relativistic. On the other hand, for k smaller than k non-relativistic, this would just be delta C. Okay, this is just the simplest way to see it. Of course, again, in order to follow the neutrino fluid, you have to solve the Boltzmann equation for it, because it has also a non-trivial anisotropic stress. And so you have to go to these Boltzmann codes that I mentioned yesterday, but for us, it's more than enough. And also this effective time dependence and so on and so forth. But you see now, if you take the power spectrum of this, you will have a suppression of the power spectrum on large scales, on large scales, that is small scales, with respect to the larger scales. And this suppression, since the power spectrum is the square of this guy, would be linear in f nu. So what I'm plotting here now is the ratio between a power spectrum in which you have considered massive neutrinos, K, with respect to a power spectrum in which the neutrino masses are equal to 0, K, as a function of K. Okay, so this ratio is 1 at small k's, that is at large scales, and then will be depleted. This is a linear theory result, which I'm qualitatively describing. This is more or less this non-relativistic scale, which is something about 0.2 h inverse megaparsec. But what is the important point is that this effect, this depletion, is proportional to f nu, and a good fit to the result of the data is something like -8 f nu. Okay, where in this f nu you count all the neutrino, the mass. I mean, depends on the sum of the neutrino masses. In particular, f nu is given by sum of the neutrino masses divided by, say, order 90 h square electron volt. Okay, again, divided by 1, or say, divided by omega matter today. Just to give you a flavor of how big is this effect, if you have some of the neutrino masses of order 0.1 electron volt, which is the ballpark in which we would like to be sensitive if we want to measure actually the scale of neutrino mass, then the effect, this delta P of P over P, is of order almost at 10%, 0.07. Okay. So it's not a small effect, but it is at rather small scales that, as we will see tomorrow, are already in the nonlinear regime. I mean, if you want to compute this effect reliably, you cannot trust quantitatively the form of the power spectrum that I just showed. Actually, for instance, you can see in n-body simulation with neutrinos that, okay, this ratio follows more or less the linear perturbation theory result at some point, but then it grows again. And this is a fact that you cannot easily describe of course, you completely miss in linear perturbation theory, but you can also easily describe by analytical method in beyond, I mean, the linear order. But okay, the message is, okay, neutrino masses so we are sensitive to neutrino masses. That is not a small, it is not a small effect, but the precise computation of this effect requires some effort. But the good news is that, okay, as a result of many analyses, we can say that next generation galaxy surveys are sensitive to the relevant range in neutrino masses. I mean, we will be able to measure, to see a positive detection of the neutrino masses effect, even assuming that we have the lowest possible masses still allowed by experiments in, say, 10 years, more or less. Okay, other questions at this point? No? Okay, so now I'm starting to discuss something which will take us a little bit closer to reality, because up to this point, what we have seen is a power spectrum of dark matter, okay, at the linear order in perturbation theory. So I just set aside for the moment the problem of nonlinearities, but there is, of course, an urgent problem that we will never measure the dark matter power spectrum by looking at dark matter, but we only can rely on tracers, on galaxies, on Lyman alpha, on some baryonic physics, which we believe up to some point should trace the distribution of dark matter. So the problem, which in cosmology goes under the name of bias, is how well do the tracers that I use think about galaxies, just to fix the ideas, how well do they trace the underlying dark matter field? In the dark matter field, we have all the cosmological information from inflation plus, again, all this physics that we have described up to now. The point is that on top of this dark matter, now you have a galaxy formation, and how can we treat this problem of the distribution of galaxy with respect to the dark matter one, okay? So bias. One is, this is one of the complications that we have if we want to infer properties of cosmology from galaxy measurements. So the problem is the following. We can somehow model or compute the distribution of dark matter particles, if you want, but we observe galaxies or tracers, okay? So how do the two distribution are related? Well, of course, here there is a lot of complication because nobody understands perfectly the physics of galaxy formation. So, but still we can say something. Still, I mean, if we are looking at the galaxy field at very large scales, we can see some big simplification. So, for instance, the first answer that you can do is simply to say, okay, the galaxy density field will just be up to some scales a constant times the dark matter density field. Okay? Why? Well, because probably where there is more density, as also somehow said before, if there is more density, then the probability of forming galaxies will be higher. So let us try with this kind of ansatz. Well, remember that what we are interested in is not the density, but the density fluctuation. So if you write this guy as some average, if you are interested in the galaxy density contrast, then it is just ng minus the average value divided by the average value. And since everything here is proportional to A and multiplied by the respective quantities for the dark matter, here, this one the A constant will simply simplify in this ratio. So if this is the situation, then the galaxy density field will simply be equal to the dark matter density field. Okay? But this is not what we find. Actually, if you look at different types of galaxies, different tracers, and you see, and you take the ratios between this, the density contrast of these different type of galaxies, you see that these ratios are not one, they change. It means that different galaxy types have different formation formation processes, which will lead to some dependence on delta G to delta M of this form. So what is proportional is not the galaxy density field, but it's the galaxy density contrast that we can hope to model. I mean, this is the minimum thing that we can do. We can hope to model as a proportional to the dark matter density field. This B is called the linear bias. Okay? As we will see, in reality, this relation is much more complicated. It is not only non-linear, but also non-local, and it also has an amount of randomness in it, because we can never exactly understand where a given galaxy will form. But this is the simplest ansatz that one can do. And a way to motivate this ansatz actually was beautifully explained by Kaiser more than 20 years ago, which is the following. So imagine to visualize the galaxy density contrast as some random process. No, this is X. So I would have regions. Okay. Regions in which are overdense or underdense with respect to an average, which I call 0. Then the idea is that, so this is just the zero point. The idea is that galaxy formation does not track exactly this distribution, but galaxy formation requires some threshold in the density, in the overdensity. So if you have some threshold that I put, for instance, here, so this is, let me call it delta threshold for the galaxy G. Of course, this threshold will depend on the galaxy type. Then you will only form galaxies where the dark matter density field will be higher than this threshold. Okay. So you see that if you now take the average of this, basically the galaxy density field is not tracing the whole dark matter field, but only the peaks. So what you are doing actually when you are doing galaxy statistics, what you should do the statistics of the peaks of a Gaussian distribution. And you can see that at the first order, actually what you have is at very large scales, scales in which you are forgetting about explaining the details of the formation of galaxies. The first result that you get is actually that delta G is linearly proportional to delta dark matter. This is something that you can also expect from more general considerations like the equivalence principle. Because at the end of the day, what matters in gravity is the gravitational potential, and actually what matters are the terms which goes as the second derivative of the gravitational potential. Physics cannot depend on the gravitational potential itself, the value of the gravitational potential, cannot even depend on the first derivative of the gravitational potential, because it is just a coherent uniform force. So when the gravitational potential starts to become important is when you get at least two spatial derivatives. And again, if you want to form a scalar, the only possible scalar that you have is just the Laplacian of it. So the dependence of both this field, dark matter and galaxies, will always be somehow proportional at larger scales to the Laplacian of the gravitational potentials. So what is left? Okay, of course, this dependence is exactly fixed by the Poisson equation, because remember, it relates the Laplacian of the gravitational potential with the dark matter density field. This relation will, at the very large scales, be just, I mean, okay, let me do it. So imagine now you go to Fourier space. So what you expect is a relation of these types. Let's say B0 plus B1 k square over kg square k square phi. This is the gravitational potential, the Laplacian gravitational potential that is delta matter. And what is kg? Kg is the scale at which the physics of the galaxy formation becomes relevant. So what I'm saying is that if you are looking at very large scales, you can neglect this first, derivative corrections, and what you are left is with some coefficient that you can compute in general. It will be also time dependent, but it is scale independent in the very large scale limit. Okay. Okay, this is for the linear order, but indeed there are complications. You go to nonlinear order, and I will try to at least summarize the results that have been derived in the last years on this complicated problem of nonlinear bias. Okay, if there are no questions, let me just list another, in this case, easier problem, which is, however, very relevant from the observational point of view. So the goal here is to reconstruct the dark matter, say the galaxy density field. I want to know where are galaxies, because from that I will then smooth a little bit the distribution and then derive a field. So it's crucial to know where galaxies are. So how do we know where a given galaxy is? Of course, we cannot measure directly. We are looking at the light from this object, from this galaxy, and then we are using the Hubble law to infer the distance. Okay, so basically we infer distance of a given galaxy. I will be very sloppy here by the Hubble law, where this is the velocity of the galaxy, and the velocity of the galaxy is related to redshift. So basically, we measure redshift. From redshift, we infer velocity by the Doppler effect, and by assuming a given cosmology, which enters here, we know what is the distance, and we put this galaxy in our theoretical or observational lattice, and we know this galaxy is here. Okay, but there is a problem here, as you can imagine. And the problem is here. I mean, what I'm interested here in for deriving the distance of the galaxy is its velocity due to the Hubble expansion. But imagine that I have two galaxies at the same distance from me. I'm here, but one of them is his proper velocity is going outside, and the other one is going towards me. Okay, so these two galaxies are at the same distance from me. It means that according to the Hubble law, due to the expansion of the universe, they have the same amount, say, of VH, which is the velocity due to the expansion. But then what I measure is not VH. What I measure is the sum for each galaxy of this velocity and the proper velocity, the velocity that the galaxy has because there are some gravitational potential here, so it wants to move, basically. So if this is the situation in real space, then in the observational space, actually what I see for the galaxy, for the first galaxy, say galaxy A1, I see a velocity and then a redshift which is less than the Hubble redshift. So if there is less total redshift, I will infer less distance. So I would say that the galaxy 1 is here, while galaxy 2 is here, just because of this observational effect, because they have two different velocities. I mean, there is a component of peculiar velocity which sums up with the Hubble velocity, and in the redshift space in which I measure distances, the two galaxies are far away. So this is what I call redshift space. And this is, okay, real space. Okay, as we will see, this is a problem, but we know, at least at large scales, how to deal with this problem. Not only, but dealing with this problem gives us some information, some very precious information, because it gives us a way to know about the velocity and how the velocity grows with time. That is to say, how the structures grow in time. Okay, and okay, now I will be a little bit more specific, but you can understand that the handle that we have is looking at different orientations. Okay, because this effect is there only for velocities which are aligned with the line of sight. Now, if you're looking, if you have two galaxies which have velocities which are orthogonal to the line of sight, of course, I don't have any deformation. So by looking at the power spectrum now with different orientations, I mean, I'm looking at the power spectrum along the line of sight and across the line of sight, I can switch on and switch off this effect. And so I can learn about velocity, the velocity field. And velocity field brings a lot of information on the way fluctuations grow. I just give you some slightly more details. So the idea is the following. If V is the total velocity, then it has an Hubble component, which is proportional to the real position, the real distance, plus a peculiar component, okay? And we infer the position of a particle just by taking V divided by H. So you see that the position of this particle is its real position plus the peculiar contribution to redshift, which gives, I mean, a shift of this order. Moreover, let's take Z as the line of sight. Then what counts in this case is just the Z component of the velocity. Sorry. So the component, as you see, is orientated only, I mean, it only depends on the z component of the velocity, as I just explained. So the idea is, okay, this is the real space, this is the Redshift space. How does the power spectrum in real space compare with the power spectrum in Redshift space, which is the one that I measure? Okay. We can see this relation as a mapping, which is actually it is, between real and Redshift space. So the question is, how is the density field in Redshift space related to the density field in real space? I don't put time here just to be a little bit more simpler in the computation. And the idea is simple. I mean, you just do this mapping by a delta function. And you integrate the tracks. So basically, this mapping, what it does, it takes every particle and it moves in the apparent position that it has because of this Redshift space distortion effect. Okay, now I want to compute the power spectrum of this guy. The power spectrum of this guy, I have to compute, I have to take I have to write this as an average and the fluctuation, and the same for the density contrast in real space. I do Fourier transform. We'll now skip some passage. What you see is the density contrast in Redshift space in Fourier space. Okay. You can do the math, is not difficult at all. Okay, I wrote it in this way to show you, okay, that actually this is a nonlinear effect already at this level, no? Because we have the density contrast here for dark matter, but then because of this delta function, when I do the Fourier transform, the velocity goes to the exponent, basically. So I have infinite orders, if you want, in the velocity, which is also a perturbation in my expansion. So I just stop at the first order. I mean, I just stop, I expand this exponential, and I just stop at the first order in V. And so what I see is that the density contrast in Redshift space now takes an extra contribution besides the delta of K, which is exactly given by the velocity. Okay, I'm looking at some galactic field. So this is the Redshift space for this galaxy G, galaxy type G. This is the real space, in a sense, not Redshift space distribution for the galaxy field G, plus I kz z of K divided by H. Okay, so there are two contributions. One is the density field for the galaxy, and one is the velocity field. Okay, and this velocity field, since velocity, okay, velocity field can be expressed of K as I kz over K squared theta of K, where this theta of K, if you remember, is the divergence of V. So remember, the velocity field is entirely described by its divergence. So in Fourier space, we have this relation, which I put here, okay, which tells me that it is given by the galaxy density field minus kz square divided by k square theta of k divided by h, okay? Okay, now the last part, the last thing I want to do, I want to relate theta, the divergence of the velocity field with the density field. And this is very easy. This is just the continuity equation. Delta dot is equal to minus the gradient of V. This is just the linear density, the linear continuity equation, which simply tells me that the way, I mean, the reason why perturbation grow is because matter is flowing towards a given point. No? This is just continuity equation. The only thing that you should notice is that this one is not delta G, but it is the dark matter density field, and this is the true density field. I mean, sorry. Okay, this is an important point. This is, I have a density, I have a continuity equation both for dark matter and for galaxies, but then I assume the equivalence principle, that is to say Vg is equal to V. So I have a way which is given by equivalence, dictated by the equivalent principle to relate, sorry, to relate the velocity field of the galaxies to the density field of dark matter. Okay. Okay. The way in which the density field of dark matter grows is d of a naught. You remember we computed yesterday, we showed yesterday this growth factor. This gives me the time dependence of the dark matter fluid. And what I do here, I compute the time derivative as the derivative with respect to the logarithm of d. Okay, I can relate the time derivative to the derivative with respect to the logarithm of the growth factor times this quantity, which is the logarithmic growth of d with respect to a. This quantity is called the growth function. So what we have here is a result which holds in linear perturbation theory. HFD is equal to minus theta. Or as you see from here, delta is equal to minus theta over hf, where I repeat, f is the logarithmic derivative of d with respect to. Okay? So this is where the cosmology information resides. It tells me how fast are growing the perturbations in this particular cosmology. So it goes here. So as you see, here I have h over f. So what I should do here is to put f in order to have this, this quantity here. Then this theta over hf, this minus theta over hf is just delta. So what I have here is plus f delta. Sorry, it was kz square over kz over k square. Okay. And then finally, and this is the last thing, I remember that delta G is BG times delta. So this is DG divided by BG. Okay, I put everything together. So you see, this is the proportionality between the density field for the galaxies in rest space and that in real space. You just have this factor 1 plus f over b, which is angular, which depends on the angle. Okay. So when I take the power spectrum, what I see is that the power spectrum now is two-dimensional dependent. It depends on the modulus of the wave number, but also on mu, where mu is just k times z. I mean, is the scalar product between the direction which I'm looking at and the z direction, and the direction of the wave number which I'm considering. So it is the power spectrum for the galaxy in real space, which is only k dependent, times the square of this quantity here. Okay, and notice that all this part here is scale independent. So there is just a proportionality in k, which however depends on mu square, and has information on this ratio f over b. Okay, f is crucial because it has information on cosmology. It tells me how fast are the fluctuations growing, and b is the bias for that type of galaxies. And so by measuring the power spectrum in different orientation, or by taking Lagrange multiples, I can, in principle, disentangle this mu dependence and then measure this f over b for different galaxies. If I would be able to do it for different tracers, then I would measure f of b for different galaxies and then factor out the b and know about the real f, the real growth function of the fluctuations. Okay, how much time do I have? 10 minutes. Okay, if there are no questions, let me just finish with the two more things that we should take into account if we want to compare our computations with measurements, or if you want at some point to design a new galaxy survey. So what are our observational limitations? I mean, unavoidable, if you want, observational limitations. One was already mentioned at the beginning of my first lecture. One is cosmic variance. If you want, I can also call it volume variance. It means simply that I have a finite, when I'm observing the sky, I will always observe a finite volume in the sky, which, if you want, at most can be the Hubble horizon, but in general will be smaller than the Hubble horizon. So this induces an unavoidable statistical error in my measurements. I want just to estimate now what is this error, and as you guess, it will be an error at large scales, which will limit the precision with which I can measure the power spectrum on very large scales. So if you remember the definition of the power spectrum, okay, the power spectrum is just this ensemble average of the delta modulus square at different Ks divided by the total volume of the survey, if you want. Okay. So if you're survey as a volume, say L cube, just to fix the idea, imagine you have a box, okay? Then the smallest frequency that the smallest wave number that you can observe is K naught, let's call it K naught or K fundamental. It's just the 2 pi over L. This is the fundamental mode that you can observe by looking at the volume of order L to the cube, okay? And if you want, in Fourier space, the smallest volume that you have is kf to the cube. So the idea is, if I measure my power spectrum at a given k, how many of this fundamental cube are contained in a given bin in delta k? So this number is just n of k. Suppose I measure the power spectrum at some wave number k with a binning from k plus delta k. And I integrate over the 4 pi, over 4 pi angular integration. Okay, so how many of these fundamental volumes are contained into this shell in Fourier space? This tells me how many independent realizations of the power spectrum do I have at the bin k. And this is a very simple computation. It's just 4 pi k square delta k divided by the fundamental bin, which is k fundamental cube. Okay. Well, it means that if my measurement of the power spectrum at this bin will have a statistical error, which typically will go as 1 of the square root of this number. If I am assuming that I'm following Gaussian statistics. And if you put numbers, you see that it is just, if you put what we just saw, it is just 2 pi square k square delta k L to the cube. Okay, what do we do with this? Okay, we can solve, we can answer a simple question. Imagine I want to measure the BAOs, the power spectrum at the BAO scales at 1% accuracy. So how large, at least, how large should be my survey? How large should be the volume of my survey? Okay, so what you do, you just put 1% here. You put for k the BAO scale, which, as I said, this is something like 0.05 H inverse megaparsec. And okay, you can be generous and say delta K is of the same order of K. And what you get is that your volume in this case should be something, the length of your box, the length of your box should be something of order of 1,000 megaparsec over H. So you need 1 gigaparsec cube volume. You have to observe 1 parsec gigacube volume if you want to measure the power spectrum at this range. Okay. Finally, and this is the last of the complications. Real life complications. You don't have only problems at very large scales, you have also problems at very small scales, due to the fact that we want to measure a field, but actually we are measuring discrete objects, points, galaxies. So we are sampling a continuous field with some discrete points, discrete objects. And this will induce another unavoidable error, which is called shot noise. A way to see it, remember the definition of correlation function. So this is the definition of correlation function, where now this n is the distribution of discrete objects. So I call this quantity here theta discrete, and it is given by this quantity here. Okay, I will show you that this quantity is a problem even if you have no real fluctuations. What I'm saying, assume that now eta of x is just, okay, some eta bar 1 plus delta of x with delta equal to 0, okay? Then what you see, that this quantity is just the expectation value of n squared divided by the square of the expectation value minus 1. And this is even in the case in which you have no real fluctuation in the field. And again, if you assume Poisson statistics, the expectation value of the variance is not equal to the expectation value, to the square of the expectation value, but there is a fluctuation which gives, as we saw before, 1 over n bar to the power 1/2. So this is even in the case in which you have no fluctuations, due to the fact that this density is finite, you are sampling your field with a finite number of objects, you have a contribution to the discrete correlation function. So actually your real correlation function, so your real correlation function, which is a discrete one, or your measure, sorry, correlation function, will be the continuous one, which is the quantity you are after, plus 1 over n bar, no, this is 1 over n, sorry, because this is just a square. 1 over n, delta d, sorry, and I'm looking at it at x equal to y. So this effect corrects the distribution the discrete distribution function when it is considered at one point. So this is what you are looking after, and this is what you are observing. I mean, you have a singular contribution that goes like 1 over n. So it doesn't seem to be so scary, but if you now go to Fourier space and you compute the power spectrum, the Fourier transform of the delta function is just a constant. So it means that in Fourier space, the power spectrum that you infer by Fourier transforming this object, the discrete power spectrum, will be the continuous one plus 1 over n, where this is the average number of traces that I have in my survey. And you see this is a scale-independent contribution to the power spectrum, which is a white noise, which is called shot noise. So this has very important consequences from the practical point of view, because if you are going to measure some power spectrum as a function of k, you remember the power spectrum is something like this, but then there will be the shot noise, which would depend on the density. So before you start doing computation for a given galaxy survey, it's better to know what is the density, the number density of the object that you are going to compute, because as you see, at some point, the shot noise will overcome the signal. So there is no point in computing the power spectrum below, at scales smaller than a given scale, where the shot noise starts to become dominant. Okay. So I think I can stop here.
Okay, thanks. If there are no questions, we stop here and then reconvene at 6 for the discussion session. So are there any questions now that are urgent, or we ask them later?